Today we're pleased to welcome Rob Penny from Southern QA. He will share his perspective on quality assurance of steel structures in New Zealand. We've got a pretty good attendance here, Rob, so obviously quite a interesting topic. Mark McDonald recently worked with Rob and his team on the Te Kaha One New Zealand Stadium in Christchurch. Te Kaha, most of you are aware, is a landmark project for Christchurch, the last major piece of the kind of public rebuild. 30,000 seat, fully enclosed stadium, designed to become the city's major venue for sport, entertainment, and cultural events. Mark McDonald provided a broad range of engineering services for the project, including structural, civil engineering, facade, building services, acoustics, wind engineering, sustainability, and building science. My name is Terry Dawson. I'm a technical director here at Mark McDonald, a structural engineer, and I was part of the team responsible for the structural design and construction supervision of the stadium. From a structural perspective, Te Kaha presented a particularly demanding engineering challenge. The stadium has a 175 by 210 metre long structural steel roof, and that clear spans over four, it's been a while since we worked on that project, four structural steel and concrete framed stands. The project team had to balance structural efficiency and seismic resilience with the practical realities of steel fabrication, erection, temporary works, program, cost, and the requirements of a world-class sporting and entertainment venue. The design of the roof and stands incorporated ductile elements to respond to Christchurch's significant seismic demands. Structural steel was delivered by local firm like Auckland local Graysons. They did one of the stands and quite a lot of secondary steel around the building, plus Chinese firm Jingong Steel. And those different procurement sources pose different quality assurance challenges in addition to the challenges of the building structure itself. Southern QA's involvement with Te Kaha is particularly relevant to us today. The company was appointed as the compliance auditor for the project, providing independent oversight of quality and compliance associated with the stadium's steel construction. Southern QA is a Christchurch founded but New Zealand company with a history dating back to 1987. Did AI get that right, Rob? Yes. 1987. Over nearly 4 decades, it has developed into a specialist inspection, testing, and quality assurance business with operations throughout New Zealand, and a few of Rob's colleagues have visited here from Auckland and Hamilton offices. And expertise spanning non-destructive testing, welding inspection, third-party inspection, coatings, fabrication, and technical assurance. The company has worked across major infrastructure and industrial projects in New Zealand and internationally. Rob himself brings more than 45 years of experience in non-destructive testing and inspection. He's been involved in the development of technical standards and documentation within the industry and is qualified to level 3 in NDT. Is that right? Okay, that's an AI one again. He has also held senior technical and management responsibilities within Southern QA, including his role as director and technical manager. Rob will give us a perspective that we don't often get to hear in the quality fabrication, inspection, and assurance processes behind the successful application of structural steel in New Zealand. I personally had the pleasure of touring Jingong's Chinese factories for a week with Rob and other members of the design and construction team, and assure you that he is a very engaging speaker. So you won't be bored tonight. Rob has travelled up from Christchurch for this presentation, and he and his colleagues will, so we're going to aim to finish around 7 and allow 30 minutes of a good session of questions. And those could be directed to Rob and his colleagues. And I think, as Megan mentioned earlier, we'll moderate that online in the room. And you're welcome after that, if you'd like to stay back and have some one-on-one chats or whatever, then we'll be staying for that too. However, without further ado, please welcome Rob Penny from Southern QA.
Thank you, Terry, for the kind introduction. It is an absolute pleasure to be here tonight. Gobsmacked a bit by the amount of interest in our little corner of the engineering fraternity. And thank you to Engineering New Zealand. I believe there are some Materials Society people online as well, and so many here in the room to listen to my particular brand of torture, really. So thanks all for coming, and thanks for making this possible. It's a real privilege. Terry's sort of summed up. I might just leave that there. Is that okay? Can everybody down the back hear me? Is that all good? Yep. So here's some topics I'm gonna try and cover off tonight. We'll have a brief introduction, which mostly Terry's done. Some QA principles. What does QA do? Materials. I'll talk about the challenges of the quality assurance of materials as they relate to steel structures in particular, fabrication and welding, other of steel structures, other manufacturing methods I'll touch on briefly, like forging and casting, erection and site welding. Then I'll get my soapbox out and stand on it and talk about bolting, one of my passions, and a little bit on protective coatings and what can go wrong with protective coatings. Of course, protective coatings are assuming a more and more important role as part of a structure. As soon as you touch into fire protection, it becomes a structural element, not an architectural element. So that's an interesting. So we'll try and keep to the time.
Yeah, had a little kick those sausages.
Yeah. Well, there's quite a lot to cover, so we'll have only have a very short sort of scratch the surface of the subjects. So part one, introduction. QA generally, what is it? It's the fence at the top of the cliff. That's what it's designed for. QA is about controlling the inputs to manufacturing processes. Back in the day, if you go back far enough, QA was sort of synonymous with NDT. But now you have hospitals and hotels and schools, and everybody has a QA program. And they're not necessarily QA, some of them are just more quality management systems. Okay, but okay, what happens when it goes wrong? What happens when instead of building a fence like that, you build a fence like that? That goes wrong. What happens when it goes really wrong? Badly wrong. You end up with this. Instead of having a fence at the top of the cliff that catches most of the risks, you end up with a whole bunch of ambulances at the bottom. I've worked on far too many projects where that has been the case, and we'll touch on a couple of those tonight. Here's one that was overseas, a small, I don't know, is everybody familiar with the Hyatt Regency Kansas City walkway? Some are. A small detail change. They were suspended platforms, one above the other, with tie rods from the ceiling, and a small detail change of how those rods went through the transverse members, the transom members that held the walkways up, was altered. And the engineer didn't catch the implications of it. And this is what happened. Over 100 people were killed. Closer to home. Anybody remember that one? Southland Stadium. There was plenty of blame to go around with the Southland Stadium. It didn't have a single cause like the Kansas City one. They admitted in the report that they couldn't identify all the causes. design, fabrication, erection, materials. There's blame to go around every step of the way. Monitoring, QA or the lack thereof. You know, I heard an apocryphal story about Southland Stadium that the roof trusses were so lightly designed that they had to put temporary bracing on them so that they would support their own weight to be erected. I'm sure the design engineers in the room would think that was probably a little bit abnormal. QA principles. Why and how does it go wrong? What's the problem? Why do we get these failures when we're doing QA? The first is commercial considerations. Everybody's trying to build to a budget, erect to a budget, and so on and so forth. The recipe of QA, it's a bit like baking a cake. You can have all the right ingredients, but if you put them in the wrong order and beat them and cook them wrongly, the cake won't work. Or you can have all the right processes, the quantities, the timing, everything is perfect, but you swap one ingredient out for another one, the taste is not so good. Technical inertia. We've always done it this way. That's the way we've always done it. Why would we want to change? Until we had all the earthquakes in Christchurch, not many buildings in New Zealand had ever been subjected to their design loads. When they did get subjected to their design loads, some of the results weren't so flash. Assumptions of supply quality, particularly with overseas procurement, this is an issue. We live in a developed country. Our supply chain has a lot of credibility, a lot of veracity, and we generally trust the people that are within our supply chain. But the minute that you go offshore to buy products, you can lose that. You can lose that confidence in your supply chain. Normalization of deviance. Has everybody heard this term before? It's a common term in aviation. What it means is you do something slightly outside the rules the first time and you get away with it. So you do it again and you do it again. And after long enough repeating that, you end up with a deviation from the norm, a deviation from the standard that is accepted as normal. Normalization of deviance. And that occurs. There's no question that occurs in steel structures. So talking specifically about steel and structures, some fundamental elements of the QA process of assurance of quality, compliance of the materials, quality systems for the fabricators. The quality systems, ISO 9000 series standards applied to a steel fabrication and erection environment is covered in a standard called ISO 3834. I think it might be actually ASNZS ISO 3834. SNZ, there's a representative from SNZ that I spoke to earlier. They run a steel fabricator certification program based on this standard. So quality systems, many of our bigger fabricators, like the ones mentioned earlier, like Grayson's, for example, have steel fabricator certification. ITPs and third-party inspection, an ITP, inspection and test plan. That details every QA check carried out through a manufacturing process. Fabrication and erection, compliance of welding, bolting and coatings. We'll touch on those a bit later on, what goes wrong with those. Overseas or non-certified supply. One of the things that happened in the Christchurch earthquakes was that small firms that had never done a construction category 3 job suddenly got a construction category 3 job, and the QA requirements were a bit beyond them in many cases. And you know, it was a supply and demand issue. Quality systems and the ITP. Fabricators will be certified to ASNZS ISO 3834. They will have quality management systems in place. But those quality management systems only reflect general systems. The crucial aspect of project QA, as we found on the stadium, Terry, is the inspection and test plan. How are those general quality elements applied to a specific project? So you're drilling down to much more detailed levels. The ITP defines the application of the certified quality system to the specific project, and it does it in much more detail. So there's a number of elements in the inspection and test plan, and some of the things that are often missed are the specific clause or criteria. It's not enough to say your welding shall be in accord, or your welder qualifications shall be in accordance with AS NZS 1554. It gives you 4 different ways to qualify your welders. Which one has the fabricator chosen? Because, for example, you can't weld a CC3 or CC4 project using AS NZS 1554 welder quals. You have to have ISO 9606 ones. So the details matter. Specific clause, criteria, and responsibilities, hold points, who's going to perform the check, the test or inspection, who's going to review it, who's going to witness, who's going to review the documentations, who's going to witness certain checks, what are the deliverables, what documents are going to come through in the MDR, the manufacturer's data record, that prove compliance of the structure, that demonstrate compliance of the structure. So that's what an inspection and test plan does. So there's some basic introductory principles that will come through through the topics. Materials. Materials compliance for steel structures first. NZS 3404, our design code, it permits materials to a range of structures, to a range of standards, I should say. Other standards, other than the ones specifically listed in 3404, will likely require specialist material substitution reports. The acceptance of the standards is based on the statistical distribution of the testing in factory production controls and initial type testing by the steel mills. A different overseas standard will have a different way of calculating their confidence intervals and so on, and saying what those confidence intervals are allowed to be. So you may require, as well as thicknesses, rolled section dimension, proportions, all of those things are different in different standards. So as soon as you get offshore procurement outside the materials specifically approved in 3404, you can run into trouble. Welding of steel structures is very limited under AS NZS 1554, which is mandatory for welding to AS NZS 5131. So the welding has to be carefully controlled if the materials are not AS NZS materials. You basically have, and we worked on a project where we were auditing, and they did a full set of weld procedures using an overseas equivalent grade to the AS NZS grade, which hadn't yet arrived at the factory. And they worked them up and did all the tensile tests and sharpies and everything, and they're all no good, because you cannot use a EN grade material to produce your weld procedures for AS NZS grade materials. They waste a whole lot of money. That is very specific. AS NZS material standards, 3678, 3679 parts 1 and 2, 1163, 1594, so on, they require ILAC endorsed reports for material conformance for mechanical and chemical tests. That's the primary verification. Some overseas standards don't require that level of accreditation for the testing laboratories. Some non-compliance examples on materials. We all remember the reinforcing mesh, Waikato Expressway. There's plenty of public domain information about that and materials non-compliance. Other ones that we've come across recently, incorrect stainless grades. 304 doesn't last long in a corrosive environment. And we've seen several jobs where it's been erroneously installed and it's lasted less than 12 months. 350 LO and 350 L15. Dan and I and Terry were talking about this just before because it was an aspect of the stadium that had to be worked through. That L0 and L15 materials don't automatically meet the seismic requirements of S0. We've still seen fraudulent material certificates in the market. So material certificate that was supplied for a project that for a number of projects. In fact, a batch of material came in from offshore, and one of the merchants in New Zealand bought all the steel, and when you tried to trace the material, the mills all said it's not ours. Stainless steel pipe fittings with incomplete weld fusion. Is that a material or a supply or a welding issue? API line pipe extruded with a minimum thickness, and some of the thicknesses were below the minimum thickness. And the merchant said, we've got a certificate saying it complies with the API specification. Not our problem, it's your problem. How does that work? Not sure. Decarburisation of bolt threads. We struck a case a few years ago where the heat treatment of the bolts was in an imperfect atmosphere with too high an oxygen content and decarburised the threads, and you couldn't achieve the TB tension on them without stripping the threads. Stuff like that. We get a few examples. This looks like a pretty good multi certificate. Looks like all the other ones we get. I've removed identifying marks to protect the innocent because it was certainly nothing to do with the mill. But it was a completely fraudulent test certificate. Here's another one, the carbon equivalent value. When you're welding, the carbon equivalent value is quite important. The carbon equivalent value on this particular material certificate, I hope everybody can see that okay. Might be on the back, might be a bit tricky, but you'll see that there's a big red fail here. This is off our database that you input the you can upload from an Excel sheet or manually input the values on the material test certificate, and it spits out whether the chemical and mechanical values pass. In this case, up here, you can see the CEV limit is 0.39. And the CEV for this particular set of chemical values is 0.40. When we went back to the supplier, this was an Australasian supplier. When we went back to the supplier, it turns out that their spectrograph was not sending the correct formula, pass-fail criteria across to the reporting software. So it was calculating the value correctly, but then not sending, using a different formula to calculate the pass-fail criteria. So it said that it correctly said that it was 0.40 on the material test certificate and then said it passed. I spent quite a bit of time looking for rounding errors to find out why my database was spitting out the wrong answer. Turns out it wasn't spitting out the wrong answer at all. Here's an interesting one where the grade, I just mentioned this before, 350 L15 grade, 60 millimetre thick, and you've got to pass. Because L15 has no requirements for RELRM and RELFY values, for the ratio values of the material to ensure seismic ductility. So it's fine, meets the grade requirements. But hang on a minute. As soon as we tick the C3 box in the database, which says it has to be a maximum of 0.8 RELRM and a maximum of 1.33 RELFY, suddenly it's got to fail. So it's difficult. And one of the challenges sometimes is that you may not know which elements have to be structural seismic category 3 or 4 when you purchase the steel. Can be a bit tricky. Now one of the things I've loved about working in engineering all these years, working with all these fine people like you guys, is that engineers are always looking for answers, looking for solutions. So I love the solution-driven approach to engineering. So here's one that is a solution. This is a good a compliant mill certificate. It's got the CNAS logo up the top identifying who's done the testing. It's got the grade and the size and thickness and all the values, and that's what we should see on a good material certificate. Okay, fabrication and welding. Sort of issues do we get here? What could possibly go wrong? This one's not that old. That is a dairy silo. The way that they're manufactured, what you see there at the bottom, all of this is a skirt. So they make a skirt, and then they sit the silo base in it and weld it all the way around. And that's how the structure stands up. You can see the hold down bolts and so on. In this case, that weld attaching the skirt to the cylindrical part of the silo had a lot of welding defects in it, and eventually they developed cracks, and the thing went, and then it was full of milk, so it tipped over, and that wasn't my sound effect then. And it tipped over. So that was pretty serious. So the sort of things that can cause that: generic ITPs, no ITP, maybe no inspection done, or the incorrect percentage, or the wrong method, unacceptable procedures, excessive heat input. Excessive heat input on stainless is particularly damaging. Missing welds. In some of the cases with that silo, the weld was almost missing because it was fused to the cylinder but not fused to the top of the skirt, which is a bit thicker and harder to melt and fuse in. In some cases, excessive bending on structural steel elements, where they might have not read the specification in terms of the limitation on the bending radiuses, and they end up work hardening and get some issues. I've worked on projects where they've actually had to do some stress relieving because the materials were excessively bent. Poor welding examples. What do we get in poor welding? This is relatively recent. These are weld defects. Now, this is what's called a boat sample, aptly named because in a longitudinal weld, you cut the weld preparation out in a boat shape, like a dugout canoe shape, and then you cut it down the centre line. So this is showing the defects on the centre line of the welds. And this is called chevron cracking. It's characteristically at 45 degrees to the surface. It's very unusual, but it was a major issue. And there could have been a number of contributing factors. And the most likely one is a very excessive heat input to the weld. But in this case, this was a pressure item for the power industry, and it had to be completely remade. It was made in China, and this is what was found after it arrived in New Zealand and was installed. So they had to uninstall it. The last time I saw parts of this item, it was on the back of a truck heading to the scrap metal dealer in Christchurch, and I just happened to drive the other way. I know what that is. So the cost was immense. Project delays, removal costs, extra surveillance on the remake. It was horrendous. Multi-story apartment building in a seismically active area. It just happened to find non-compliant welds during a different audit visit for a completely different project. The building was half built, 20 stories high, had to be disassembled, all the parts taken away, cut out and re-welded, brought back to site and re-erected. Poor welding examples was certainly a contributing factor in the Southland Stadium collapse that we saw a photo of before. Here's a stainless steel pipe fitting. There's a whole bunch of them had to be cut out and replaced after installation because they had this type of defect in them. The lack of root fusion. So the weld bead has wandered off, hasn't fused one edge of the root. Not ideal. Getting it right. Let's move on. So that solution that engineers love. Getting it right. Fabrication and welding. Approval of the ITP, the inspection and test plan. Appointment of competent persons. Correct application of procedures, including things like the welding consumables, the heat input, and so on and so forth. Fit up. In-house QA and QC, checks and records. Who's checking the fit up? That's your welding supervisor's job. Is he competent to do that? Is he doing it 100% of the time? Those sorts of things. Certified, ISO 9712 and accredited ISO 17025 inspection and testing as the last step before you get to the fence at the top of the cliff. And in many cases, is a PS3 required? Does the inspection company have to provide a PS3 to confirm that the inspection program outlined in the ITP and the engineering specification have been completed and that there's no outstanding non-conformances? Other manufacturing processes. Casting and forging have a particular issue. Before any of you were born, and I started my career in inspection, there were steel foundries all over New Zealand. There were three big steel foundries in Dunedin alone. There was a couple in Christchurch. They were everywhere. Forging shops, people doing spin casting, centrifugal casting of stainless pipes. There was all sorts of manufacturing going on in New Zealand. Most of that's gone. Most of that's not here anymore. So the expertise that was part of the intellectual property of all those companies that were doing that work, it's disappeared. Not there anymore. People have all gotten old and retired. The same, and here's an example. This is a forged flange. So how does a forged flange get shrinkage defects in it? Because the blank from which it was forged had shrinkage defects in it. So it's a problem. Disappearing technical knowledge. That should have been, I would have thought there would have been evidence of that in the casting from which they were forging flanges. But there we go. Here's another one. This is a large casting, bronze, made in bronze. This was tested and passed. This was tested by ultrasonics and passed. When I tested it, about 70% of the area of the huge ring that was cast in 4 pieces and welded together. The reason we found out about these defects was because it was made in 4 segments, this giant washer, this giant ring, and they were welded together. And we had to x-ray the welds. And when we x-rayed the welds, we found all the shrinkage in the adjacent parapet. And when we had a look, about 70% of the area of this ring of casting was like this. It was completely non-compliant. Not only is the knowledge for how to do the casting disappearing, so is the knowledge for how to do the testing. Moving on, erection and site welding. Erection and site welding present a unique set of issues, a different set of issues. All of the same things that apply to shop welding apply to site welding. And then there's a few more. I don't think these are the only issues. I'm only highlighting the ones that apply only to site welding here. So the non-compliance factors that tend to pop up, erection pressure. They want to get the building up, costing money. There's craneage and all these other things that are going into. Everything relies on the previous progress. So sometimes QC checks are missed. Sometimes the builders come along and close things in and we can no longer get to them. There might be a column like that with some steel inside it. Can't get it anymore. We often see with site welding inadequate or poor MDT for the same reasons, because sometimes things don't get seen. Procedures unsuited to environmental conditions. If you've got a fabrication shop, usually you've got a controlled environment you can do your welding in. You can do your cutting. You can do your painting. You're on site, much more difficult. Environmental conditions are critical, especially for coatings. Welding and coatings, the two of the specialist processes that rely on the environment. Missing welds, poor quality welds, just generally people rushing it and maybe not doing a good enough job. Difficulties with working at heights. How high did you get on the stadium, Terry? You probably didn't get very high.
Dan went higher than me.
How high, Dan?
50 metres.
Oh, only 30.
At 40, I think, to the
Oh,
top.
40, yes. Yes, our guys had to do some bolt tensioning checks and some welding checks on the 56-metre job right from ground level. They had 2 cherry pickers big enough to reach the roof from ground level. And there are difficulties with working at height. Everything, particularly if you're welding, how do you get your gas up there for preheating? How do you get your welding equipment up there? It's a big job. So who's checking? This is the sort of stuff we sometimes come across. There's a bit of a defect there when your end of your steel rule disappears into the groove. Coating's not going to work very well on there, is it, Sean? That's one of the issues. That one is just some probably relatively small gussets, and the ends of the welds aren't cleaned out properly. And you've got these horrible looking lacquer fusions, and you've got all these also horrible chunks of spatter. The problem with that is just as big for the coating people as it is for the welding people. Your coatings are not going to last 5 minutes on there. Bolting. What could possibly go wrong? I'm not aware if bolting had any impact on the Southland Stadium, but if it was as good as everything else they did there, it probably did. A quote from Georg Albrecht, who's a name worth noting, and have a look at him on LinkedIn. He's one of the world's gurus on bolting technologies. A quote from him: "Torque is nonsense in terms of a metric of a bolt's tightness. Torque does not define tightness. It is only an input in an effort to achieve tightness, the clamp force." ASNZS 5131 has extensive checking and documentation requirements, which are often not met for bolting. They just do that. Often there's a lack of effective procedures and a lack of supervision on the people doing the bolting. And often a lack of training, poor understanding of definitions and requirements. I still get people asking me things like, but if we use this part turn method to achieve tension in the bolt, how do we know we've used the right torque? It's about as sensible as saying, well, I'm doing 100 k's down the motorway. How do I know I'm using the right throttle setting? You're using the right throttle setting because you're doing 100 k's. It's simple. So it's a very poorly understood subject, extremely poorly understood. Quality and compliance issues on site for bolting, joint designation. These all need to be defined before you can perform the connection tensioning with the bolts. Joint designation, bolt grade, size and length. Lubrication. Has the snug type been achieved before you do the part turn? What are the markings? How are the markings put in and the markings after part 2? Documentation. What documentation needs to be provided for each connection? For example, with a job as big as the stadium, I keep harking back to the stadium, I'm sure Terry doesn't mind. With a job as big as the stadium, bulk batches became important. Because if a bulk batch was subsequently, by our testing, for example, proven to be non-conforming, we needed to know where every bolt in that batch had gone. Otherwise, we had to take out every bolt in the entire structure. So bulk batches, recording of the bulk batches on every connection became really vitally important. Poor fit up will never deliver joint performance. Here's one here. That one it doesn't matter. You can make that bolt as tight as you like. And that joint will never perform because there's no friction between the two faces that are meant to be sitting hard in contact with a major clamping force. In this case, you're never going to get the clamping force because if you look closely, there's a fillet weld in the back there that's stopping the bottom plate, the top plate from getting in contact. What could possibly go wrong? Wind turbine. This is from Tokuyama in Japan. And this is a direct quote from the accident report analysis. For this Tokuyama wind turbine, the cause of the accident is not the matter of design or material, but it is because of the reduction of high tension bolts pre-tension force. In a flanged connection, like that one, how can the bolts reduce their tension over time? The only way they can reduce their tension is if their tension was variable at the beginning. So that is my pointer to what might have gone on at Tokuyama. Vestas 3 megawatt turbine in Sweden, bolt fatigue blamed for collapse. The root cause of the bolt fatigue was insufficient clamp load. There was no check that the desired clamp load had been achieved. The operator was inexperienced and not adequately trained. You've got flanged joints like that, and if those bolts are done up to a reasonable level, a reasonable percentage of their yield point, that joint will behave and will behave very strongly, way beyond the adjacent tower material. So the joint will never be the weakest point. So how did that tower fail at the joint? You get variable joint tensions because they've done them up with a torque wrench maybe, and the most heavily loaded bolts see the load and they stretch, and that transfers the load to the adjacent ones, and they see the load, and then next thing you've got enormous cycles. Every time the tower sways, you've got cycles going through all the bolts. Sooner or later they get a fatigue crack and it falls over. Bolt fatigue. Root cause of the bolt fatigue was insufficient clamp load. So the bolts failed in fatigue. It's not just fatigue loaded structures that we have to worry about. Here's one after the Christchurch earthquakes where those bolts have opened up a huge gap. Now, if those bolts were properly TB tensioned, that joint would have stayed together. But because they weren't, it was doing this in the seismic events, stretching the bolts, creating a big gap. Moving on a little bit to base plates. I mentioned this to somebody before. If you have a back nut, if you have a leveling nut in a design like the one on the left, and you part-turn tension the nut on the top, the only bit of the anchor rod that's tensioned is the bit inside the plate. Nothing else has got any tension. So instead of a leveling nut, what about putting some leveling shims that the bolt will move through as you tension the bolt? And then packing the grout around that. What about, is there a bond breaker on the anchor rod that's set into the concrete? Because if there's no bond breaker on the anchor rod, the only bit of the bolt that's the rod that's getting tensioned is the bit above the concrete. Potentially the bit above the grout, if it's a grouted one. So in this event, and we've seen towers where this has happened, where they've had this arrangement and they've got a fatigue crack just in there because the tower's in the wind and it's just going like this. But there's no preload, there's no tension that has to be overcome before the cycles start in the threaded rod. So bond breakers in the embedded portion and shims to level it if you have to level it, shims to level it while you pack the dry pack grout. And then tension that from afterwards, once it's all done. And you will have a constant, even tension on all the bolts that's developing, say, 70% of the yield strength of the anchor bolt material. So you can't possibly get a fatigue crack until the wind loading is so high that you've overcome that 70% preload of the bolts. And I would suggest that probably designers would design it that way. Would they, Terry? They would, at 70% preload, the wind loading would never exceed it. Okay, so that's one of my little soapboxes. I love bolting and I love dealing with bolting issues. Protective coatings. We'll cover this briefly, and it'll be great to have some questions, one-on-one questions for Sean later about coatings if you've got any concerns about coatings. Preparation. Protective coatings failures. Pretty shiny sort of surface there for that paint to stick to. Might not work so well, eh? Environmental conditions. What might have happened here? I've seen water-based intermescent applied on columns like this in circumstances where the building is not yet enclosed higher up. And you come back a week later after they've applied this very expensive water-based intermescent, and there's puddles of water-based intermescent on the floors. And there's no water-based intermescent left on the columns. Horses for courses, environmental conditions. Bolts and joints. What happened here? The bolts were put in after the paint had been applied and it cracked all the paint around them, and a few months later you've got all this rusting happening around the bolts. Failures, sort of failures you can get, lack of adhesion, defects such as peeling, blistering and holidays, early breakthrough corrosion, where the zinc's not thick enough and it's sitting on site and suddenly it's all gone rusty again, and particularly in corrosive environments like near the sea and ports and places like that. Big problem. Delamination. Delaminations can be caused by a number of factors. It can be environmental factors. It can be incompatibility of the different systems that are being put in between layers. It can be temperature related. There's probably all sorts of things that Sean can talk more authoritatively about. And some root causes: poor surface preparation, surface contamination, environment, incompatibility of the layers. Sometimes these are written into the specifications. A lot of the paint specifications, unlike engineering specifications, which are written by engineers, it's often the paint suppliers that write the specification for the coatings. And they may or may not have the knowledge. Doesn't hurt to get it reviewed. Incorrect application and curing. Temperatures, humidities, those sorts of things. So getting that right. Let's move on to protective coatings. How do we get them right? And a lot of the elements here are very similar to what we would do with welding. Clear specification requirements, a clear and agreed ITP, applicator capability review. Have they done a job before? Have they got the right equipment? Can they actually, have they got the right abrasive to put the right profile on the material before the first coat goes on, etc. Applicator QC, how many checks of thicknesses are they doing? Monitoring by a third-party inspector, potentially, very important. An independent cross-check. So the applicator QC gets reviewed. If it all looks okay, a sample can be taken by the third-party inspector or an independent inspector that verifies that their QC readings were actually what was needed, and a final sign-off. Okay, a couple of points. How are we doing for time, Terry? Oh, we're just about done. A couple of interesting points. The role of the third-party inspector is different to the role of the compliance inspector. Often a compliance inspector will be engaged by the fabricator, and his job is to perform such tests as are outlined in the specification or the ITP. Third-party inspector will often have an audit role, like we did with the stadium, an audit role overarching that, which will ensure that all of those people doing that second-party inspection or compliance inspection are actually doing their jobs properly. It depends on the size of the project, what's appropriate, size and complexity. So I've got a list here. We'll skip those of the sort of the detailed functions that a third-party inspector will do. Anybody's got any questions, they can certainly come and see me about that later. And then we've got independent or compliance inspection, and that's a different role again, typically engaged by the fabricator, not by the engineer, client, or the client's representative. And the compliance inspection is about ensuring that all of these specialist processes, such as welding and coatings, meet the requirements of the standard. Typically, minimum qualifications apply for compliance, the compliance inspection parts. And on a big job like the stadium, there'll be a lot of moving wheels, different people. We had 3 separate auditors for the audit team, and then our local team in Christchurch did the compliance inspection. So we had both welding, coatings, and materials specialists and NDT specialists on both teams. Entirely appropriate to have IANZ accreditation, ILAC MRA accreditation for the people doing your compliance inspection. Just a footnote on that, ILAC and IAF. IAF are the international organisation that have previously done overseen accreditation of certification bodies, people doing 9,000, 14,000, etc. certifications. ILAC have been the people that have done the laboratory and inspection body accreditations under standards like 17020 and 17025 and a whole lot of others. Those two international organisations have merged, and they will soon be recognised as global ACI. So at some stage you will see, instead of the ILAC CNAS logo, and in some cases an ILAC MRA logo, CNAS will remain, but ILAC MRA will be replaced by global ACI MRA. So things change. Finally, pretty much finally, overseas procurement issues. What do we see as the differences there? Design, materials, drawing and welding symbols. The symbol for a full penetration weld in China and the symbol for a full penetration weld in New Zealand are different. The New Zealand one means a partial penetration weld in China. What could possibly go wrong? Fabrication tolerances can be different. Welding procedures and qualifications require specialist review to determine which ones can be adapted for a New Zealand design project and which ones can't. And the inspection processes and procedures are very different in the rest of the world, particularly with respect to steel structures, because steel structures in most of the world include their own requirements for how the NDT and inspections are done. Whereas in Australia and New Zealand, that is not in the steel structures welding standard or design standard. It's in a separate Australian standard. So the requirements are quite different. Damage during transit, and up the top, contractual differences in legal jurisdiction. The fact that overseas procurement often requires you to pay for the product before it leaves the country of origin. So that can be difficult to get remedial work done. Summarising, in all of the areas discussed, coatings, working backwards, coatings, welding and fabrication, inspection, material procurement, and so on, latent defects can exist. By definition, latent defects are invisible. You don't know that they're there. Latent defects might be there. The best thing to create that good fence at the top of the cliff is good QA, supported by independent expertise in specialist areas. And you get a good fence at the top of the cliff. Some designers will have specialist expertise. Some paint applicators, some welding companies, fabrication companies, erection companies, inspection companies. Everybody will have specialist expertise. If you can bring that all together in the ITP, you'll get the good fence at the top of the cliff. There are still far too many ambulance call-outs to a big mess at the bottom. Okay, and I think that's me done. Thank you very much. I'll have a little drink.
Thank you, Rob. Right on time. No, that was very good. Thank you. It was it's one of those subjects where you don't know what you don't know, I think, and being able to call upon experts such as yourself, particularly for, particularly complex projects. Yeah, we certainly benefited from your presence and your team's presence on our project, that's for sure. How are we doing online, Megan? Are there any? I can see a bit in the chat there.
Yeah, we do have some questions that have come through. I can read some out to start with, or you're welcome to go through the room if there's a bunch in there.
Maybe. Oh, somebody's got their hand itching. Maybe start us off with a couple online, and then we'll throw it to the floor.
Beautiful. So I'll start from the first question in. So question for Rob: can imported steel in New Zealand be accepted based on the ACRS certificate, or is testing by an IANZ accredited laboratory required?
Generally speaking, if the steel supplier comes from an ACRS is an ACRS accredited supplier, there's not normally any requirement to do any further testing here in New Zealand. That's a risk issue really for the engineers. They may have specific critical elements that they feel should be cross-checked.
All right, thank you for that. Hope that's answered your question there. If not, please pop something into the chat. The next one I have is, if the knowledge to casting is disappearing and so is testing, where can we go to learn this to apply it?
Next question, please.
Sorry, that is your prerogative. Happy to move on if you'd like.
That's a very wide-ranging question. In terms of the testing of castings, I think there's probably not many people that are still have the knowledge for testing. Where IANZ accredited for testing of castings, and we've very much limited the number of people that are authorised to do castings. In fact, I think at the moment I'm still the only one in our company of 40 odd people that is fully authorised to do all the testing on castings.
So you're not allowed to retire then?
Well, I think we've got some guys that are pretty close. So, you know, we've been doing a lot of work together to get them up to speed on castings. But yes, so the testing side, in terms of the foundry side, the actual casting technologies, the best people to talk to are probably the, I think it's called Casting New Zealand or Casting Technology New Zealand. There is an industry body for casting technologies.
Mike McDonald did a recent tour of the Glenbrook New Zealand steel mill. I highly recommend doing that. If they're very welcoming to visitors, and they put on a lot of tours, so you can go watch some casting.
Yes, yes.
I'll just take a question from the floor. You had your hand up earlier.
I was just wondering how much of an issue is people forging documents, and you mentioned that it happens. How often is it being caught that happens?
It's not common, but it happens. And if it happens to the extent that we're seeing it on items that really have a known requirement to meet a certain standard right from the get-go, how much is it happening on things that nobody checks? We don't know. I suspect it is a much bigger problem than you would think. I know that there was some work done a few years ago on, and I think there's been Building Act legislative change around dezinkification resistant brass fittings for plumbing use. And 25–30% of the ones that are sold retail in New Zealand are not, they're stamped DZR and they're not. So you put them in a chlorinated water supply and they don't last very long.
I had one break the other day and flood my bathroom. Any other questions from the floor? Okay, maybe have you got more online there, Megan?
I do have a few that have come through. So the
Okay.
next question we have here is, are cracks, shrinking defects permitted in structural weld?
I'm going to pass that to Dean.
Under SP grade? No.
Yeah, SP grade generally not.
Yes. Yeah. Yeah. GP grade, which is just a general purpose, stop start credit cracks are allowed.
Okay, so if we're talking about a shrinkage like a stop start crack at the end of a weld run, then they are not permitted under structural purpose category welds, but they are permitted under general purpose category welds. More extensive cracking than that, no, they're not permitted.
All right, thank you for that. Another question just in, please interrupt me if there's more from the room, but can you please explain in more detail how to achieve snug tightness and the part turn, and also how to check the bolts and what percentage of bolts are checked?
Right, okay, that's my favourite topic. Snug tight is a terrible term. I should have, it's a great question and I should have mentioned it earlier. Snug tight is the term written into the standard, but and you sort of think about snug tightening being, oh, you put a spanner on it and you sort of you nip it up a bit, you know. But the definition in the standard for snug tight is the full effort of a person on a standard podger spanner. So podger spanners are a specific length that goes up with the diameter of the bolt or the across flats dimension of the nuts, and they get bigger. So it's the full effort of a person on a standard podger spanner. So it's full hand tighten.
Is that a standard person?
Yes, it's any person. So the reason that they've used that definition is it's a very simple one to apply. And yes, you could have an all black front rower of 130 kilos who could be pulling on it and pull on it a lot harder than Mick Belt, for example. Stand up, Mick.
Not only that, I'm incredibly weak for my small size as well. So it's a bit subjective, all of that, isn't it?
So, you know, most of us are, you know, that are at my age, certainly You know, we tend not to be as strong as when we were young, but it doesn't matter. A snug tight bolt, if a person has tightened it as tight as they can get it, that is tight enough. If it's a TB or TF connection and we're doing a part turn, the variability in the snug tightening doesn't matter. There's another definition of what is snug tightening. That the plies being closed by the action of the bolt must be fully in contact. No gaps allowed. So it doesn't matter how tight you've done the bolt up. If you can still see the bolt shank through the gap between the two plies, it is not snug tight. And at that stage, you have to think about inserting shims or milling the end of the plates or whatever to make them fit better together. Because often you'll get moment end plates, for example, are classic for being like that. You can go round the connection multiple times to try and successively pull it up, and you should find that you will achieve the snug tightening. When you come to the part turn, then typically for a bolt whose nominal length is less than 4 times its diameter, we're talking about a 1/3 turn of the nut in relation to the bolt head. You can achieve that 1/3 turn any way you like. There is no prescription for how you achieve that turn or what the torque value will be of that turn. You can do it any way you like. You can use a podger spanner and a long piece of pipe and a couple of front rowers, or you can use a hydraulic spanner, electric spanner, a torque multiplier, whatever you need to achieve the 1/3 turn. The principle of the 1/3 turn, since we got onto that subject, is that the part turn will reliably take the bolt into the yield range. Once you reliably take the bolt into the yield range, the amount of clamping force on the plies that you're bolting together is no longer a function of how you've tightened them. It's a function of the material. It's a material property. So the consistency that we get with part turn tensioning is very, very good. You know, there's often a range of only probably 10% between the tightest bolts and the loosest bolts. But other instances occur where if you use torque control methods, the best sample I've ever achieved on a set of bolts using torque control methods was one where the loosest bolt was 1/3 of the tension of the tightest, using identical torque on identical bolts. 1/3, a 3-to-1 difference. It's common that is 8-to-1 or 10-to-1. So torque control methods, one of the principles, if you're using part turn methodology, if you've got enough torque on the nut to reach the yield point, you've got enough torque to break it. There's very little, it's a pretty flat curve on the stress strain curve. So does that answer the question? I hope it does.
I think it does. Let us know in the chat again if not. So the next question in here is, how important are shop drawings, and is it acceptable risk to have an engineer or company sign the shop drawings and the PS4 when they did not do the initial PS1 design? Is regulation changing in this space? Not sure if you'll be able to answer that one, but
I'm going to boot that one to Eric.
Just so an engineer has done the PS1 and then another engineer is reviewing the shop drawings and doing the PS4. Yeah, that's a curly one. It's definitely not advisable and not preferable, but I could see circumstances where that might occur. I think the engineering companies involved need to take care, and certainly there should be a degree of conversation and communication between them. But that's probably a bit of a legal question. But I would say not advisable, but probably not impossible. Quickly
All
move
right.
on to the next question.
Yeah, we can leave it at that. Moving on. Next question in here. Sorry if I said any of this incorrectly. What are your thoughts on using squirter DTI washers for determining tension of TB and TF bolts? Can they be relied upon?
Yes. That's a very easy question. I've seen them demonstrated and they achieve exactly the result intended. What you can't do that people get a bit confused about is mix and matching part turn methods with DTIs, the squirter washers. You either use one or the other. You don't try and mix and match them, you'll get completely confused.
All right, thank you. The next one again, possibly getting onto the legal side as well. What do you look for in a certificate to determine whether it's fraudulent or legitimate?
There's going to be telltale signs sometimes. We get used to particular mills and we have, many thousands of certificates in our database, and we can pull up previous certificates issued by that mill and look for particular signatures or stamps or other telltale signs that indicate that it might not be a perfect, a different. We've seen certificates where it's clear that somebody has twinked over this value and typed over or printed over the top of it, and you can, and certainly if you can get the originals, if you can get a good scan of the originals, it can become a bit more obvious. So we look for all sorts of things, and you sort of get a bit of a feel for it after a while, after you've looked at your first 1,000 or two.
Can I interject a codings question? Is it Sean
Please.
taking care of codings? In the slides, one of the coding defects was called a holiday.
Yes.
That didn't sound too bad to me, but apparently that's not a good thing.
Yeah, it's known as a discontinuity in the coating. So it's a pathway that'll go back down to the substrate. So yeah, so what we do is we use Australian standard 3894.1 or 0.2, which is the high voltage testing or the low voltage sponge testing, to be able to find if we do have these discontinuities in the coating that go down to the substrate. Yeah, those are holidays.
The term came because somebody once, Mick knows the story I think better than I do. The term came because somebody spotted a patch with missing paint or something and said, oh, the painter had a wee holiday here.
And so in Europe, they're actually called holiday detectors.
Yeah.
The voltage, the high voltage, except for the Americans call it a Jeep because that's a noise it makes when it activates a spark. But which becomes really confusing when someone says, can you run that Jeep tester over the pipe? And they get in their Jeep and drive over the pipe.
I see a few more bolting questions for Rob. You've got some potential friends online
Could
there,
be
Rob.
here at
Any questions from the room you want to go to, or I can keep going here online?
Yeah, good point. Anybody? Are you allowed to ask a question yourself?
Yes, I can. Rob, can the bolt stretch be measured ultrasonically?
Yes, it can.
There we go.
That is exactly how we do it. The bolt monitoring that we do and that we did, the previous question also included a question about how many do we sample. Typically, it's a very small percentage because the actual post-tensioning measurement is not non-destructive. You take the bolt out and you measure the change in length on release, and that tells you what its tension was before you released it. But you then have to throw that bolt away and replace it. So we tend not to do a very high percentage. A complex project might have 1% if you're lucky. So it's really as much as anything, it's a sort of a QC process rather than a QA that we are doing quality control on the number of connections. And how we do it is we have this very accurate ultrasonic instrument. It's not an ultrasonic micrometer. It won't measure the length of the bolt accurately, but it will measure its ultrasonic length in inverted commas. And that is how the ultrasound behaves along the length of that bolt. Okay, and then it will save that trace, and then you'll release it, and that trace will shift that will sort of shift like this on the screen, and the two peaks, it'll lock onto the two of the peaks. It's actually not the peaks, it's actually rectified signal, so it locks onto the X crossing points and tells you how much the bolt length has changed between reading A and reading B, with about estimated uncertainty of measurement in the sort of 5 to 10 micron range. So if you're looking for 200 micron extension, it's great, it's fantastic. And then Hooke's law and some of the calculations, the geometry of the bolts, the length of the bolt, and so on, will then tell you what the design, what the load or stress in the bolt that equates to. We're only measuring the length, but the maths does the rest.
Can I ask by a show of hands how many consulting engineers are in the room? Oh, so a good majority. Because I was going to ask a general question on how you feel the quality of specifications are from consulting engineers, and if you had any comments about, you know, should we all be using master spec, for example, or
no, I think the quality of the specifications that we get for our jobs is pretty good. I think it's developed, you know, quite well in the last couple of decades, and certainly specification reviews are something we provide to engineering consultancies pretty much gratis up front. We're more than happy to cast our eye because it's
that's your fence at the top of the cliff.
Yeah, absolutely. It's only our portion of it is a fairly small portion, and we know exactly where the pitfalls are and how to spec it properly. So we're very happy to do that for consultants.
Long as you mentioned the consulting engineers, just a general question about the Christchurch Stadium. What was the involvement of the third-party QA company in the design stage?
I'll just repeat the question. So for the Te Kaha One New Zealand Stadium, what was the role of the QA?
In the design stage, the involvement in the design
So the
stage.
QA party, I guess that's yourself, Rob, in the
Yep.
design stage.
Yeah, pretty much nothing. Until the specification is written, we don't really have any involvement at all. Our job is to be the gatekeeper of the specification. And there was probably some design issues that popped up later where we suggested alternative solutions. But I don't think we would have known about them at design stage. They were things that were difficult to manufacture, maybe.
It was a fast track kind of stage delivery project. So as we were building parts of it, we were still finishing the design on others. So there was some overlap and some interaction there.
I mean, the ITPs were like in line with the method statements prepared in that project.
Remember that the ITP is the fabricator's document.
Yes.
It's not the designer's document.
Yeah, but there is during the construction there is a method statement related to the ITP. For example.
Yeah, definitely. I mean, we were in China putting the finishing touches to the ITP before there was any material arriving. So we were involved early enough to do that. So at that stage, we were reviewing and auditing their welding procedures and welder qualifications and traceability methodologies and their NDT training and the people that were going to do that and so on and so forth. So yes, at the ITP stage, there's a lot of involvement from us, but at the strict design stage, no.
Megan, how about the last question on the chat there? Looks interesting.
Yes, one that's just come in now. With offshore fabrication increasingly relying on third-party inspection, what are the key indicators that the inspection regime itself is genuinely independent and effective, rather than simply providing another layer of documentation?
Wow. Yeah, that's a minefield. That's a very good question. And it is a minefield. Particularly, I mean, anybody's welcome to have a look at what can go wrong. My favourite expression tonight, what could possibly go wrong. Have a search for the Geelong AFL Stadium welding problems. Have a look for that. and you'll see what can go wrong when the third-party inspection agency didn't do their job properly. And, you know, one of the things that happened with CMUA, with Te Kaha, was that the problems that surfaced in Geelong were on a B6 Wattpack job, who were the main contractors for Te Kaha.
Yeah, I recall the auditing system for CMUA needed an org chart of its own. It was
That's
so
right.
many layers and so complicated
Absolutely.
across different parts
Yep.
of the.
And so relatively early in the project, B6 Wattpack came to us directly. They were our client. They came to us directly and said, we've had this problem at Geelong. We cannot afford another one. It didn't quite say we don't care what it costs, but that was there was a certain amount of that behind that. We want you to make sure there is zero possibility of a repeat. And we achieved that, I'm proud to say. Hugely proud to have been involved in the project, and very proud to have got the outcome that we did with it. So that was a good one.
Just a few minutes left, maybe a couple more from online, Megan, unless anybody in the room.
Yeah, I've got 3 more online in front of me. I'll have a
Okay.
start with one. How many thread protrusions clear from nut do you accept? Previously, we have had differing opinions. 1 clear thread to 3.
There is no opinion. The standard says there must be 1 clear thread outside the nut.
All right.
No,
Hopefully that was
there
a
is
quick one.
There is a strict requirement, much more importantly, there is a strict requirement for threads under the nut. And I once had an instance where an erector was putting together a building and they said, these bolts are breaking, there's something wrong with them. So I shot down to the site, it was in Christchurch, fortunately. I shot down to the site and had a look, and they only had 2 threads under the nut, and they were trying to do a third turn on a bolt that was about 70 or 80 mil long. So all the yielding was taking place in the root of 1 thread, and they were just twisting the nuts off with a section of bolt attached to them. So very important. For a third turn, it's a minimum of 5 threads under the nut. That can include the washer region. For a half turn, it's 7 threads under the nut. So good question. But only the mandatory requirement is only 1 outside the nut.
All right. Hope that answered the question below it as well, possibly as well. So the last question I'll ask is, can BIM and integrated digital systems improve traceability and QA in steel fabrication? And would you recommend fabricators make this a significant investment?
Yes. I've seen overseas some pretty good traceability programs where every piece that gets cut is laser etched with a unique ID number. Where barcode stickers are put on every piece that's cut. And broadly speaking, when you get to a substantial project, you have individual materials. So a piece of plate comes in and is cut into different pieces. The different pieces then have a part ID, a PID. Those PIDs are then collected together. 2 of these and 1 of those and 5 of those and 3 of them, and they're made into an element which has an EID. They have a pretty simple sort of 3-letter acronym system. So you've got material IDs, part IDs, and element IDs. And so there's some great work being done overseas. And when you have workshops that are on the scale of Thai Herrick and Jingong Steel, and the one in Indonesia that's also a steel mill, GRP, those sorts of digital technologies are really useful. Do we have anybody big enough in New Zealand that it's sort of really important for at this stage? I would say probably not. But it's certainly something that's going to become probably easier and cheaper as time goes by.
I think one more question then, Megan. I noticed quite a few people online have got their hands raised as well. So I'm sorry we won't be able to get to all your questions, but feel free to look up Rob and his team at Southern QA, and I'm sure they'll be willing to chat with you another time.
Absolutely.
But one more question then, Megan, last one.
I think the last question here was partially answered by Rob before, but I'll repeat it anyway, can clarify if needed. Can you please explain the minimum thread requirement after tensioning a TB connection? Why are there different requirements, i.e. 5 threads below nut when the length is less than or equal to 4D?
Okay, because it's not when it's 4D, it's when it's a third of a turn versus half a turn after snug tightening. So a half a turn is going to stretch the bolt further, and therefore you need more threads to prevent excessive necking or excessive stress occurring in too fewer thread areas immediately under the nut. I hope that it's not really about the diameter and length of the bolt, it's really about the amount of part turn.
Okay, well, we'll call a halt to it there. Thanks. A lot of great questions there. Very engaging questions. Thanks again to Rob for presenting today and his team for travelling here, and for all of you as well. Really good attendance today in our office and online. Thank you. I think there's still a bit of cold pizza if anyone's still a bit peckish. We'll be hanging around for a little bit if anyone would like a further chat. Otherwise, yeah, thanks again for attending, and we'll see you next time.
Thank you very much, Terry.
Thank you, Rob.
Thank you very much.